In this topic, we'll cover the kinetic theory of gases and show that with the ideal gas law and some relatively simple Newtonian mechanics, we can gain some pretty amazing physical insights into the thermal properties of matter. So kinetic theory is the study of the microscopic behaviour of molecules and interactions which lead up to relationships like the ideal gas law, pressure, volume, and finally a really precise definition of temperature. So far in the course, we've stated that temperature is related to the kinetic energy, but not given the exact definition. In this section, we'll see that the temperature is equal to the average kinetic energy of a gas. This is important to help us understand why, when the party is over, the helium from balloons is lost to the Earth forever into the depths of outer space, and how a puddle dries up even when the water is clearly not boiling. So you may be familiar with the ideal gas law that links the properties of pressure P, volume V, and temperature T. The law can be presented in two forms, and I'll write them both here, just missing their middle bits for the time being. The science is the same, they are equivalent, it just depends if you want to deal with just a few moles in the macroscopic form or lots of particles in the microscopic form. I should say that P stands for pressure in pascals, V is volume, meters cubed, and T is in temperature in Kelvin. Now let's put in the values that represent the amount of substance and the constants. First, the macroscopic form, so PV equals nRT, where N is the amount of substance in moles. In case you have forgotten, a mole is 6.02 by 10 to the 23 particles. This is of course Avogadro's number, which is defined as the number of atoms in 12 grams of carbon. And R is the ideal gas constant that has a value of 8.31 joules per mole per Kelvin. Now to the microscopic form. Here we have PV equals capital N KT. This looks very similar, except we're dealing with a large number of particles instead of moles. N is the number of molecules, usually a very large number, and K is Boltzmann's constant, which is 1.38 by 10 to the negative 23 joules per Kelvin. This is a very small but important number. Just a note on the units of temperature. In these questions, when we're talking about kinetic theory, we're usually dealing in absolute temperatures. So not change in temperature, no delta T's anymore, absolute temperatures. Hence, we need to use the temperature in Kelvin. Now I think we'll make a quick aside to clearly define pressure, as this is quite important to understand. So when considering gases and liquids, or fluids in fact, and Adrian will explain more in the fluid section of the course coming up next, pressure rather than force is the most useful point to consider. Pressure is also one of the fundamental state variables used in thermodynamics. Put simply, pressure is force per unit area, or the force applied perpendicular to a surface per area over which the force is distributed. It has the units of newtons per metre squared, which is called a Pascal. Now onto the kinetic theory of gases. Kinetic theory essentially uses a conceptual model of a gas that pictures the gas molecules as little balls that elastically bounce off one another. This allows us to build up the macroscopic properties like temperature, volume and pressure based on the mass movement of these little ball or point-like molecules. There are four assumptions we need to make. They are that the number of molecules is large and that the separation between the molecules is very large compared to their size. The molecules are in constant random motion with a distribution of speeds that does not change. The molecules undergo only elastic collisions, i.e. no loss of energy when they collide with each other or the wall of a container, and the molecules obey Newton's laws of motion.